For this video, we will be working through and analyzing phasor circuits. Now, why do we need to do this? Well, phasors allow us to simplify AC analysis while allowing us to easily handle the phase relationships between voltage and currents, and finally allows us to transform differential equations into algebraic solutions. Now, it is important to understand that we will be shifting for our equipment and elements from time domain to frequency domain, and this can be done utilizing the following methods seen here on screen. Now, we will be working through various problems and solutions in order to gain a clearer understanding of actually what is going on in our analysis. So, without further ado, let's dive right in. For this problem, we are asked to convert the following equations into phasor form. Now, it is important to recognize that our phasor form is simply our VRMS at an angle of phase shift. Now, inspecting the first equation, we see that it is in standard form. Therefore, the coefficient in front of the cosine is our Vmax, and our phase shift is the 22 degrees here at the end. Now, to convert from Vmax to VRMS is simply this Vmax divided by the square root of 2. This is equal to 314 divided by square root of 2 is equal to 222. Now, this is our magnitude, and our angle is simply brought in from our sinusoidal function, 22 degrees. The following equation asks us to convert the sinusoidal function into the phasor form. Now, in order to convert from sine to cosine, we can simply subtract 90 degrees from our function. Now, same as last, we will need to convert our Vmax to our VRMS. This can be done by taking 816 divided by the square root of 2, and that is equal to about 577. Now, this can be used as our magnitude, and our phase angle is going to be 50 less 90. That gives us negative 40 degrees. That is used as our angle right here. And there we go. Both of these equations have been converted to their phasor form. For this problem, we are asked to calculate the phasor current of the circuit shown below. Now, it is important to recognize that this circuit is still in the time domain. We will need to convert to the corresponding phasor domain in order to solve. Starting with the voltage source, I see that we have a sinusoidal function. Now, this is not our standard form. We will need to convert this to a cosine function. Now, we can do this by simply subtracting 90 degrees from the value. Secondly, we will need to convert from our Vmax to VRMS in order to convert to our phasor domain. We can do this by taking our Vmax of 120 volts and dividing it by the square root of 2. This gives us roughly 85. Now we can convert our time varying voltage source to a corresponding phasor voltage, 85 at an angle of 60 minus 90 degrees, which gives us negative 30 degrees. Next, we will need to address our inductor. In order to convert our inductance to the corresponding phasor reactance, we will use the following equation. X equals J omega L. Now, our omega is our angular frequency, and that is given to us from our source, right here of our 377. This is radians per second. It is also important to note that this is equal to 60 hertz. Now, plugging in the values of J omega, which is 377, and our L of 200 millihenries, plugging in the variables and solving, we find that our reactance is equal to J 75.4. Now, to convert this to phasor, we simply take our magnitude 75.4 at an angle. Since this value is solely imaginary, our angle is 90 degrees. Finally, in order to solve for our phasor current, we can simply use Ohm's law of V over R equals I. Plugging in our values of 85 at an angle of negative 30 degrees over our resistance, or our equivalent phasor impedance of 75.4 at an angle of 90 degrees. Solving for this, we can find that our phasor current is equal to 85 divided by 75.4, which yields roughly 1.13 at an angle of negative 30 less 90 degrees. That is equal to a negative 120 degree angle phase shift. And this is in the unit of amperes, and this is our phasor current for the circuit shown below. For this problem, we are asked to calculate the phasor current of the following circuit. Starting with our voltage source, we are giving a time-varying source. We can identify the coefficient of the sinusoid as our Vmax, and in order to convert to Vrms, we will simply divide by root 2. It is also important to identify that there is no additional time shift to this function. Therefore, our phase angle will be equal to 0. Following through and converting, we now have a phasor voltage of 85 volts and a phase angle of 0 degrees. It is important to also identify that our resistive and capacitive elements have already been converted to their phasor equivalents, as a resistance is not dependent on time or frequency. Therefore, our total impedance can be written as 600 minus J 120 ohms. Now, this is written in rectangular form. To convert to phasor form is as follows. The magnitude of 611.9 at an angle of negative 11.3 degrees. Now, in order to find our phase current, we simply divide our phase voltage by our phase impedance. Therefore, 85 at an angle of 0 degrees divided by 611.9 at an angle of negative 11.3 degrees, we can conclude that our phase current is equal to 0.139 at an angle of 11.3 degrees amperes. For this problem, we are asked to calculate the phasor current of the circuit below. Starting with our time-varying voltage source, we can see that the coefficient in front is our Vmax. We will convert this to VRMS by dividing by square root of 2. That will get us a phasor voltage magnitude of 85. Next, we will need to find our angle. This can be done by identifying the phase shift of our sinusoid. However, since this is not in our standard form of cosine, we will need to subtract 90 degrees to get our accurate phase angle of 10 degrees. Next, we will need to convert our capacitive element to its phasor equivalent. We can do this by the following equation. X of C equals 1 over J omega C. Well, our C is 120 millifarads and omega is 377. Plugging in and solving and then converting to our phasor equivalent, we obtain a X of C of 0.022 at a phase angle of negative 90 degrees, since this is solely imaginary. Finally, in order to solve for our phasor current, we will simply be utilizing Ohm's law of I equals V over R. Plugging in our voltage of 85 at an angle of 10 degrees divided by our equivalent resistance or phasor impedance of 0.022 at an angle of negative 90 degrees, we are able to conclude that our phasor current I is equal to magnitude of 3,845 amps at an angle of 10 less negative 90, which is equal to 100 degrees amperes.